Welcome back to Electrons Dance. I hope you will indulge me as I dip a toe into the ocean of pure mathematics. When I was a young man just starting college, I had the good fortune to take an introductory calculus class from Coke Reed. He was a real character. First, he advised us to sell our calculus textbooks back to the bookstore and buy some colored pencils. Then he taught us the basics of differential calculus, largely using graphs of functions and a visual approach to the idea of limits. Somewhere in the middle of that first quarter calculus class, he presented what he called the bug problem and asked us to solve it before the next day's class, which I did. This problem struck me as such a cool one that over the next several years I showed it to many friends and acquaintances who seemed interested in math and had some knowledge of calculus. What I would like to do now is present Coke Reed's bug problem to you, give you plenty of time to think about it, and finally show you my solution. Let's give it a whirl. Let's start with x and y axes on a piece of graph paper. Two tiny bugs are on the graph paper. Bug A starts at the point 0, 0, and bug B at 0, 1. A very thin rubber band connects the bugs, initially stretched out along the y-axis and always forming a straight line. Then the bugs start moving at the same pace. Bug A crawls along the x-axis from 0, 0 to 1, 0, while bug B goes from 0, 1 to 0, 0 along the y-axis. As the bugs move, the rubber band sweeps across the graph, shading some points but never covering others, and finally lying along the x-axis at the end of our story. There's a boundary curve between the points shaded by the band and those it never covers. Of course, the x and y axes are the other boundaries. In terms of x and y, what is the equation of that curve? Some boilerplate. Of course, we're idealizing the rubber band as a stretchy but super thin band with no real thickness, attached to our bugs at their centers as they travel the x and y axes. If you want to try to solve this problem yourself, now would be a good time to pause this video and come back later. Some of you might see the solution much quicker than I did, but I suggest you give yourself at least an hour to mull it over in the back of your head, maybe even a day. I'll talk about some related but spoiler-free stuff for a short time now, while you find that pause button. Here's a bug-free way to think about the problem. The string art way. Let's start with the graph paper again, still with the x and y axes, but mounted to a board. Let's put a bunch of pins along the x-axis, evenly spaced from 0 to 1. Let's do the same thing along the y-axis with the same spacing, and with the same number of pins, less 1 since the axes will share the pin at 0, 0. Now let's make our string art by tying threads between pairs of pins. We'll start with the thread from 0, 0 to 0, 1. Then go to the next pin to the right in x, and the next pin down along the y-axis. We'll repeat this one pair of pins at each step, with the final thread going from 1, 0 to 0, 0. We can make a crude version like the one shown here, with not very many pins, where the relatively small number of threads merely suggest a smooth curve. We could add more pins, maybe halfway between the original ones, and then string those. As we add more and more pins and threads, the curved interior edge would get smoother and smoother, so that in the limit, it becomes the specific curve in question. Again, what is the equation of that curve? Okay, Dr. Reed, I admit it. Your way of posing the problem was better. This is it, folks. If you want to solve it for yourselves, close this video right now and come back to it later. Maybe it will take you a few minutes, maybe a day, maybe longer, but please make an honest effort. See you afterward. At first glance, this may not seem like a Calculus 1 kind of problem, but it turns out you can reduce it to a basic maximum problem, one of the first things we learn to do with differentials. For anyone who's not familiar with the idea, I'll try to explain it briefly. Feel free to skip ahead if you already got this. For a smooth curve defined by a function y equals f of x, the derivative f prime of x, or dy dx, really just gives the slope of the curve at a particular point. If the curve has a local maximum, like the hump in this example, that slope is small near the top of the hump and the slope is 0 at the peak. That's also true for values and minimums. So if you have an equation for dy dx, or f prime of x, you can solve for the x value or values where the derivative is 0, then plug that x back in the original function to get the maximum or minimum. I know the curve we are trying to quantify doesn't have such a maximum, so what does that have to do with anything? We'll get to that in a minute or so. It's going to help us to imagine some intermediate place along the x-axis, where x is between 0 and 1, partway along bug A's path. Next, imagine a vertical line going up from the axis at that value of x. Once bug A passes that place on the axis, the rubber band crosses that vertical line. That intersection starts at a height of 0, but as the bugs continue their journey, the intersection moves up and up. At some point, though, it reaches a maximum height and starts moving back down. By the time bug A reaches 1, 0, the intersection is back down to 0. The maximum height of that intersection is our function's y value at that particular x. So if we calculate the intersection height at an arbitrary point along bug A's journey, we can find its maximum at that arbitrary x, and that's the y value of our function. I'm going to introduce a couple of new variables here. Let's call the height of the intersection h. And let's call the distance bug A has traveled along the x-axis A. Let's see if we can write an equation for h in terms of A at that particular x. This time I'm going to use similar triangles and a little geometry to calculate h as a function of A and x. Okay, first let's look at the small triangle. H is the height of the vertical, and A minus x is the length of the horizontal segment. There's a larger triangle where the vertical segment is length 1 minus A, and the horizontal segment is length A. Those two triangles are similar, meaning they have the same shape but not the same size. Because the triangles are similar, we know that h is to A minus x as 1 minus A is to A. We can write that as an equation like I did here. H over A minus x is equal to 1 minus A over A. We can multiply both sides by A and by A minus x to clear those denominators, and then simplify further by dividing through by A. And we get this fairly simple equation. H is equal to 1 minus x over A minus A plus x. Now for a given value of x, we can plot h as a function of A like I've done here. And now you could see a classic Calculus 1 maximum problem has been revealed, because if we find the peak of this curve, the maximum value of h for a given value of x, by varying A, then we know the value of y at that peak, and that's the function we're looking for. So let's look at that equation for h in terms of x and A again. And remember, to find the peak of this curve, we're thinking in terms of a fixed value of x and varying A. I've got h equals 1 minus x over A minus A plus x, but 1 and x are constants as we vary A. So the derivative of h with respect to A, dh dA, is x over A squared minus 1. And at that peak, that derivative has got to be 0. So let's set it to 0 and solve for A. I've got x over A squared minus 1 is equal to 0. And that gives us x over A squared equals 1, and that gives us x equals A squared, and that gives us just A is equal to the positive square root of x. We know it's positive because of the region of the graph we're looking at. So now I can take that value of a and plug it back into the equation for h to get h max, which is 1 minus the square root of x minus the square root of x again plus x, or x minus 2 square roots of x plus 1. And that is the function we're looking for. Y equals f of x equals x minus 2 square roots of x plus 1. So that's our solution. Okay, I hope some of you out there had fun solving this problem, or at least had fun trying. I certainly enjoyed presenting it. But that's all for now. Take care.